Testing, 1, 2, 3. Testing. Yeah, we're testing. Now we're testing again. Yeah, a little bit better volume. How are we doing on time? 14 after. So I see we have a bunch of viewers, but nobody's live again. I don't understand why that is. So seven of you, hello. Looks like we have about 3 minutes until we get started. Hopefully you can hear me. About 1 minute to go. Okay, so we're going to get started now. I see we have 9 viewers, and again, nobody seems to be live. We're going to have to talk about that again next time, but at least we should be able to record everything. And make sure, if you can't get in touch with me live right now, that you send me an email or text message. I'll get back to you, promise. I haven't started correcting. That's later today, your quiz. So let's get right back to the lesson. I am going to share my screen here, first of all, so that we can get started. Okay, so you should be seeing my screen. This is where we were when things left off yesterday. We were talking about just by looking at, well, we learned by looking at ordered pairs, we should be able to tell if we have a function or not. You should also be able to tell just by looking at the graph using a vertical line test. And then the third one was this one. Even by looking at an equation, you can pretty much tell if you have a function or not. Remember why are the two X guys marked on this particular page? Well, we'd have to solve for y, and when eventually, like in number 30 here, when you add x squared to both sides, eventually you're going to have to take the square root so you can get not y squared by itself, but y. And every time you take a square root, you have to take both square roots, and you wind up with the telltale pull this over here, you end up with the telltale plus or minus. That's a dead giveaway that instead of only one answer for every x, this one is obviously going to have two, therefore not a function. Likewise, down here, the same telltale plus or minus. Okay, so now continuing, the next thing I was going to talk about with all of you is just telling domain what the domain and range of a function is. So sometimes a function is named this way. I know this looks kind of strange, but it says all ordered pairs x and y such that x is 5. Notice it doesn't tell us a thing about y. It just says x is always 5. So the domain is just 5. That's it. Domain always refers to the possible values for x. That, by definition here, is only 5. The range, what values of y? Well, notice there was no restriction on that. So notice I just said, well, it can be anything. Okay, now let's look at number 42. Hopefully you recognize that that's just a parabola. That's just that parabola sitting on the origin, but it's been lifted up 8 units. That's what the plus 8 tells us. So domain-wise, parabolas eventually get forever wide, so it can go forever to the left, forever to the right. So the domain, no restriction, all reals. But the range, since this is a parabola sitting on the point 0.08, will never get below 8. So you notice here we said all reals, but only 8 and above. So we'll practice this more, but eventually you want into that. Let's skip down. Yeah, so basically, let me just remind you, there's 3 no-nos, so to speak, that you're looking for when dealing with domain. Things that cause total breakdowns. Number 1, as you know, you cannot have a 0 in the denominator of a fraction. If you do, you don't even have an answer. It's just undefined. Number 2, we can't deal with negative values underneath square roots or under even roots. I say even roots, meaning square roots or 4th roots or 6th roots or 8th roots. Odd roots are okay. Cube root, 5th root, but it's those even roots that cause problems. And then number 3, practical considerations. These only come up in word problems. Let me give you an example. You're doing a word problem, and it asks you how many voters voted for the first candidate. Well, is it going to make any sense that when you're all done, you get an answer like 3.6? You cannot have 3.6 voters unless we're talking gruesome, what do you call horror movie, a gruesome horror movie. Otherwise, no, you can't have a decimal person. Or the final, the part of the word problem says, how big should you make the picture frame? Does it make any sense if the width comes out to be a negative? No, absolutely not. And so that's what I mean by practical considerations. So again, here are the big 3 you always have to look out for in domain. Something that could cause the denominator to be 0. You can't have negatives under even roots. And in the case of a word problem, you just have to make sure your answer makes sense and it's practical. Okay. So now let's just get into function notation. So you should all remember, instead of seeing y equals 2x minus 1, we've all seen problems like this, right? f of x equals 2x minus 1, really the same as y, but it has advantages because it shows you what has been substituted. So for example, see if you make sense out of this. This says f of 1 is 1. That means when I plug in 1 in f of x up here, the result is 2 times 1 minus 1 is 1, right? 2 times 1 is 2. 2 minus 1 is 1. Okay, so when I substitute 1, I get 1. By the way, what is that? You can think of that f of 1 equals 1 as an ordered pair. Again, when 1 is plugged in, out comes 1. So that's really cool advantage of function notation. It shows you the ordered pairs. Let's look at another one. What's f of 2? You agree with that one? 2 times 2 is 4. 4 minus 1 is 3. What's f of negative 3? 2 times negative 3 is negative 6. Negative 6 subtract 1 is negative 7. Okay. How about f of 0? Negative 1. So all of these are ordered pairs. 1, 1, 2, 3, negative 3, negative 7, 0, negative 1. Excuse me. So now what happens when we do something like this? Back to what I've been doing with each of these numbers in parentheses each time. Haven't I been substituting it in place of x? That's exactly what we want to do here. So this says, wherever there was an x in the original formula, now you need to put an x plus 1. So here I go. I'm plugging it in. 2, and in place of x, x plus 1, notice, got to be in parentheses, minus 1. And then you just basically carry out the arithmetic. And, well, yeah, just ignoring this for the moment. Do you see how it ends up being 2x plus 1? Got to blow a nose here, excuse me. Okay, so this should be coming back, I hope. What about f of z? Again, plug it in. 2z minus 1. What about f of triangle? Now, I know that you think I'm getting silly here, but I'm trying to lead you. I'm trying to lead you to see something, a pattern. Again, what do? We substitute the triangle into the formula wherever there was an x. 2x minus 1, 2 triangle minus 1. So what are you going to do with that? F of h plus x. Plug in h plus x in wherever there was an x. And you would get 2x plus 2h minus 1, right? Because you're going to have to remember that x plus h, when you plug it in, has to be in parentheses. And then when you carry it out, you do the distributive property, then see if you can and combine them. And in this case, you can't. All right. Next slide. All right, now, given two generic points, here, let me highlight these in red. You've got this first point over here and this second point up here. I'm calling this one point 1, this one point 2. And just to be generic, I'm calling this xy or x comma f of x. And on this one, we've moved over h units to the right. So this one, the x coordinate is x plus h. And the y coordinate is just, well, whatever f of that is, f of x plus h. Now, if I asked you to find the slope of this segment that connects them, what's the slope formula? Remember, it looks like this. Up there in the left corner. right? The y-coordinate from point 2 minus the y-coordinate from point 1 over the x-coordinate from point 2 minus the x-coordinate from point 1. So in our case, what's the x-coordinate from, what's the y-coordinate from point 2? There it is, right there. F of x plus h. Notice I just brought it down. Subtract the y-coordinate from the first point, f of x, over now the x-coordinate from point 2, right up there, x plus h minus the x-coordinate from point 1. Well, on top, you can't do much to simplify that. But on the bottom, x plus h minus x, isn't that just h? Okay, now this is incredibly important for all of you survey of calc students. I'm going to highlight that by putting a rectangle around it. Let me even make it red. Okay, so that's a biggie. That's called, as you can see down at the bottom, this is called a, whoops, wrong tool. This is called a difference quotient. It's really just a slope, because that's all we did on this page is use a slope formula. It's a generic slope for two generic points. But we are going to be referring to this over and over and over again as a difference quotient. So make sure you get this in your notes. You need to know this. And in fact, without that, I can't really introduce calculus to you. So we all need to work a bit on that one. All right. So how do I get my pages back? There we go. All right. Next page. So let's practice a little bit of function notation. Change to blue. You notice I have two functions at the top of the page. I have a function f, which is defined by points. What that means is, if I give you a 2, then the answer is 6. If I give you a 3, then the answer is 8. And if I give you a 4, the answer is 5. If I give you anything else, you don't know. You just have to throw up your arms. So it's kind of weird, but sometimes a function is defined just by individual points. And then over here, a more traditional definition of a function. If I give you an x, you can calculate what the y-coordinate is. So if I give you a 2, g of 2 would be 3 times 2, 6 plus 5 is 11. Okay, so let's practice now. What's f of 4? So that's asking, when you plug in a 4, what do you get for y? Does everybody see that would be a 5? Because it's right there. What's g of 4? G of 4. So now I got to use this rule. 4 times 3 is 12. 12 plus 5 is 17, right? Okay, now this one is a little bit backwards. This one says, well, if f of x is 6, can you tell me what x is? So you look over here and you say, which one has an answer of 6? Ah, right there. So what was x? Does everybody see that? X was 2. All right, if g of x is negative 4, can you tell me what x was? Well, here we have an equation. If the answer is negative 4, notice I just plugged in the answer, negative 4, and then the function. Can you figure out what x is? Well, sure, a little bit of algebra. Right, negative 3. And then sometimes you get a combination like we have in 50. And by the way, these are actually problems from the assignment. Sometimes you get a combination where we have an F and a G, and you're supposed to actually find the answers and then subtract them like we have here. So F of 3 is 8. And from that, we're supposed to subtract G of 3. What's G of 3? 14. And 8 minus 14 is? So that one would end up being negative. Hopefully you're along with me on that. Okay, next slide. So here again, I have two functions at the top. There's function f, that's an equation, and here's function g, and that's an equation. Find the following. Okay, I've got the answers there. See if you understand where I got that from. Find f of w. So that take the first equation and plug in a w for x. That's pretty easy. 3w squared minus w, right? Okay. The second one says, take the second equation, g, and plug in an a minus 5. So 4 times, instead of x, a minus 5, parentheses, minus 2. Then just, distributive property, simplify it. Final result, 4a minus 22. Okay. How about the number 64? What's f of x minus 3? So go to the first one again, the rule f. This time, plug in x minus 3 wherever there's an x. Now, you notice there's 2 x's in rule f, right? So for each one, I have to plug in my x minus 3. So you notice I've done that right here. See how I made that substitution twice? Then it's just a matter of carrying it out. And could I have even carried it out further? Yes, I could have multiplied this out and then combined. Here, let's do it. So this becomes 3x squared minus 18x plus 27 minus x plus 3. And then finally, when you combine everything together, 3x squared. Then we have a negative 18x and a negative 1x would be a negative 19x. And 27 plus 3, of course, would be 30. So there would be our final result. Okay, this one I just didn't do. Let's go to 68 down there on the bottom. So this time it says, find g of x plus h, and from it subtract g of x. By the way, does that at all look familiar? That kind of looks like half of this thing, doesn't it? Except it's g of x plus h minus g of x instead of f. Yeah, they're kind of weaning you onto doing they're getting you used to close to doing a difference quotient of your own. So anyway, what's g of x plus h? Well, take rule g, in place of x, plug in an x plus h. It gives me this. Here I actually multiplied, this out. And then it says from it, subtract g of x. So from it, subtract 4x minus 2. By the way, incredibly important, these parentheses, common student mistake, leave those out. You will get it totally wrong because with the parentheses, this becomes negative 4x plus 2, right? If you leave the parentheses off, you'll have a minus down here, and your problem will be incorrect. Anyway, why did I end up with a final answer of 4h? Well, just combine terms. 4x minus 4x, no more x. Negative 2 plus 2, no more 2's. All that's left, 4h. Okay, another problem from the assignment, I'm skipping around here a little bit, is number 27. So I don't know if you have your books handy, but the directions are evaluate the difference quotient and simplify. So all they're telling you in number 27 is g of x is the square root of x plus 3. Find the difference quotient. Now you got to remember what we talked about earlier. What's the difference quotient? That looks like this. G of x plus h minus g of x. That's the difference quotient, okay? So we got to use this to come up with this thing in the circle over here. Okay, so what do I need? I need a g of x plus h. How do you find a g of x plus h? That's simple. Plug in an x plus h wherever there's an x. Okay, that wasn't very hard. That'll look like that. Now, put the pieces together. There's your g of x plus h that we just figured out, minus the original g of x all over h. This stuff on the right isn't here yet. That's my next step. So here, let me highlight this in red. There is my difference quotient. G of x plus h here on the left minus g of x all over h. Okay, now what you see on the right of it is me realizing I can't just leave it that way. And so what we're doing is, I don't know, guys, you remember this? What did I multiply by? Top and bottom. The conjugate of the top. Remember that conjugate thing? The same thing, only without the opposite. You know, instead of here we were subtracting, here we're adding. And of course, if you do it to the top, you have to do it to the bottom. Okay, well, it makes the bottom kind of messy. And you can't really do much about it. H times that messy thing. But beautiful thing happens on the top. You get the difference of two squares. And when you take this times itself, you get, you know, this guy without any square root minus this guy without any square root. Well, that's beautiful because, all right, what's x minus x? No x. What's 3 minus 3? No 3. What's the only thing left on top? H. And notice the h will beautifully cancel with the h that we had down there. Now, you may not like the answer. I mean, it's not real pretty, but that would be the 1 over the square root of x plus h plus 3 plus the square root of x plus 3 would be our final result for the difference quotient. Excuse me. All right, let's try another one. Yeah, now, okay, I'm purposely, let me just go back. The problem we just did, I'm purposely picking problems that are more challenging. The first kind that's more, harder to do a difference quotient of is when you have a root, and that's what we just did in number 27. We had a root, square root. The second kind of challenging problem is when you have a fraction. And here it is, 1 over x minus 2. This, again, is what we're aiming for, except I probably should have just called, sometimes h, we put a delta x on the bottom, you know. I'll tell you what, just to avoid confusion, I'm going to just put an h there. Shouldn't have that in there. Okay, so once again, this is that difference quotient we talked about earlier. All right, here's what we have to start with right here. So step 1 is find f of x plus h. So take the original formula right here, f of x, and where there's an x, plug in an x plus h. Okay, that wasn't so painful. Now here's where it gets a little painful. You take f of x plus h, right here, minus the original f of x. And by painful, I mean, fraction minus fraction, and then that's over something. That's where it gets a little bit ugly. And of course, you have no choice but to get a common denominator so that these two can be brought together. And that's what I was doing in blue here. So you should be able to see that the LCD is x plus h minus 2 times x minus 2. And in the first fraction, I was missing the x minus 2. So I had to do that top and bottom. This one I'm missing, x plus h minus 2. So I had to multiply by that on both the top and the bottom. Okay. Well, the good news is now you can combine the tops because you have a common denominator. So here's numerator 1, x minus 2. Here's numerator 2. Watch what I did. I had to carry that minus out over this whole set of parentheses, so it becomes minus x minus h plus 2. Right? When you apply a negative to a set of parentheses, you must apply it all throughout. Common mistake. Got to watch out for that. All right, what happens? Well, the x's wipe each other out. The 2's wipe each other out. All that's left is a negative h on the top. And then there is what? Just one more step. And that is, we still got to divide by this h. So what's the easy way to divide fraction? Just invert and multiply, times 1 over h, which I did right here. And then the h's cancel. And final result down here in the corner. So very honestly, those are the ones that they take a little more sweat, the fractions and the root problems. So I wanted to take one of each of those. Let's look at number 71 for just a moment here. 71 is a demand function. So just so we have a little variety here. So that's a business problem. Demand, P is the price per unit and X is the number of units sold. It says find X as a function of P. So in other words, we got to solve this equation for X. Here it is. Here's where we're beginning. And we got to, instead of solving for P, we got to solve for X. So really, this is just an algebra action. But by the way, do you see why this is true? Why is X greater than or equal to 0? Simply, X stands for how many items sold. You can't sell a negative number of items. So it's got to be 0 or above. Okay. So can you see what I did in the first step? I knew I had to get this X out from under the, I had to get it out of the denominator. So let's multiply both sides of the equation by 1 plus 0.01x. That's what I did. On the right side, beautifully cancels. The left side, that leaves us this. Okay. Eventually, I want to get X alone. So I wanted to get rid of that P. So I divided both sides by P. Gone on the left, underneath on the right. Okay. Now I'm still trying to get X alone, so let's subtract 1. Gone on the left. Now, do you see why I wrote this? Why didn't I write minus 1? Well, actually, I did. But why did I write it that way? Because I knew I'd need a common denominator in order to combine it here. So that's another name. So I did 2 steps in one. I subtracted 1, and I knew I needed a common denominator, so multiplied top and bottom by P. Okay, now you can bring this together over 1P, which I did. And then what's the final step? Well, just got to get rid of this 0.01. So multiply both sides by 100. It's going to be gone over here. On top, you have to multiply by two things, right? How do you multiply 14.75 times 100? Just move the decimal 2 places to the right. And then, of course, I have to multiply negative p times 100. So there she is. We've done it. We've solved for x. You can either write it this way or this way. This shows the function notation has been reversed, but these are, as you can tell, they're both the same expression. It would both be correct. Okay, now there is another thing I need to show you. I'm not going to go through the 75. See what you guys remember about inverse functions. So given a function like we have here on the top, how can you find its inverse? You guys remember this from what, the old days? First, you put a y in place of f of x, which I just did right here. And then swap the x and y. Literally, wherever there's a y, make it an x. Wherever there's an x, make it a y. So do you see that I did that right here? Excuse me. Okay, then the rest of it is just solve for the new y. All right, so I put this x over here on the right. I got rid of the 9, subtracted that from both sides, and then, can you see what I did here? I completed the square. So I took half of 2, which is 1, and 1 squared is 1. And then, like we did before, I added 1 to do it, and I did it to both sides. This now can be written as a perfect square. Okay? And then just take both square roots and get y alone. Bingo. We've got the inverse. So what the inverse of a function is, it'll literally go backwards. Let me show you what I mean. In this problem, what's f of 1? If you go back up here, plug it in, 1 squared is 1. 1 minus 2, 1 minus 2 would be negative 1, and negative 1 plus 9. Does everybody see f of 1 is 8? Okay. Now, back here, we have, this is really the inverse. What's f inverse of 8? So if you plug in 8 here, 8 minus 8 is 0. What's the square root of 0? 0. And what's 1 plus 0? 1. So you notice how here we started with 1 and we ended with 8. In the inverse, we start with 8 and we go right back to 1. It literally inverts and sends you back. So that's an inverse. Now, a really cool thing happens on a graph when you graph a function and its inverse. Yeah, here's an original graph here. Here's its inverse. And notice I sketched in the identity function here. Do you see how if you tipped your head 45 degrees to the right, I know it's not perfectly scaled, but do you see how this is the mirror image of that, with this being the fold line? Inverses will always be mirror images of the original because they do that reversal thing. We practice one. So here's another one. Let's take a simpler function. F of x equals 2x plus 1. Can you find the inverse? Step 1. Make f of x into a y. Okay, now swap the x and the y's, which we did right here. All right, now solve for the new y. Okay, let's get rid of this 1 by subtracting it from both sides. And then all I got to do is get rid of this multiplied 2, so let's divide both sides by 2. So there's the inverse. Okay. Now, a cool thing happens. When you compose f with f inverse, and this is the only time this happens. If you do a composite of a function with its inverse, it will always turn out to be just good old x, which is the identity function. You know, I just realized we didn't talk about composite functions, so let's just quick do that. I'm going to insert a page here. Okay, so flatten this out a little bit. So let's just say f of x equals 3x minus 1, and g of x equals x plus 2. Okay? What is f of g of x? Okay, now here's what that means. The outer function here is f, right? So, but what I want to plug in place of x is this whole thing here, this whole g of x. So remember all along, what have we always been doing when we do f of? We've been substituting in place of x. So here, I'm doing 3 times whatever minus 1. Well, what's whatever in this case? 3 times, and then plug in the whole g function. So see the outer function, 3 times whatever minus 1. 3 times whatever minus 1. What's the whatever? All of g. Okay, what is that? 3x plus 6 minus 1, 3x plus 5. I apologize. Now, what's g of f of x? So this time the outer function says take whatever I give you and add 2. Take whatever I give you and add 2. Because what are we giving it? The whole function f. So notice that's substituted. So what do you get when you simplify this? Now, do you notice these two are not equal? So you cannot, there isn't a nice little commutative property for composing functions. Hey, by the way, the book writes this like this sometimes. I hate that notation. It's like a little circle, and it looks foggy to me. Yeah, I meant that as a joke, but it really is very true. This to me is not clear because some people write multiplication that way, so I don't like this notation. So whenever I do a composite, you're going to see me use this bracket notation like I did here. It's much clearer. So you can't inverse a composing problem and get the same answer. There is only one time it'll work. And that's when the one function is the inverse of the other. Then, when you compose them, they'll both turn out, and do you remember what they turn out to? Let me quick flashback. Yeah, they both turn out to the identity function x. But otherwise, unless they're inverses of each other, don't expect composites to work the same back and forth. And I'm pretty sure they're going to give you some problems where they're going to ask you to do them both ways. Yeah, you shouldn't normally get the same result, just like here. We got different results. So what if somebody asks you to prove that one thing is the inverse of the other? The only way to do it is to compose the original function with its inverse. And in fact, it works both ways. So up here, I don't want to take the time right now, but when you do the inverse of f with f inverse, you get x. And then when you do the f inverse of f, you also get x. That proves that this and these two guys are inverses. Well, they should be. This is what we did a few minutes ago on this page. No, we didn't do it there. Anyway, somewhere along the line, we found the inverse, and it does check out. All right. Yeah, this is just, let's just look at this one. Here's another example, or is this the one we just did? No, it's a little different. Here's a function f, here's a function g. Notice f of g of x is not the same as g of f of x. They're similar, but they're not the same. And the only time they will be, those composites can be flipped and equal the same thing, is when they were inverses to begin with. Okay, let me just show you that from the web page, you can go to the independent website, and I'll just show you. Here's an example I have up there. You can go look at it on your own, but it does just what I told you. You first replace the f of x with the y, then you swap the x and the y. Now you solve for the new y. So it just goes through step by step, and eventually it also shows that when you plot the original on the same graph, hopefully you can see these colors. The red is 1, and the yellow is the inverse, and the green line is just there as the identity function. And sure enough, if you tilt your head to the side, you can see that the inverse curve is just the reflection of the original. How are we doing on time here? 12:14. Yeah, this is a review question. So I'm going to put the assignment up now. I guess you already knew this. I think we told you this the other day, didn't we? Yeah, that it's 1 to 71, the odds. We're still going to have to work on this interactivity because I should have had 10 of you in here. I don't know what's going on, but I'll have to, maybe I could just ask you this. When you come to class on Wednesday, maybe if some of you have at least a couple of you, bring your laptop along, and I want to check this connectivity situation. Okay? Again, please contact me for some specific questions. At least we can do it that way this time, and then a little bit later I will have the video edited, and we'll put it up, and you can view it at whenever you want. Thanks a lot. I appreciate everybody's participation, even though we didn't have you kind of in there. Thank you very much.